For those of you who are part of the community, you know that literally on any day of the week, you can come to this campus and hear people who come from outside Princeton in order to tell us what they are doing. But we don't have that many opportunities to hear from our colleagues. So this lecture series was really created so that we could hear from our own eminent faculty. And we have a great exemplar of that today with Lynn Loo. To introduce Lynn, I would like to ask the chair of the Department of Chemical and Biological Engineering, Rick Register, to introduce his colleague. Rick.
Well, thank you, Shirley. I think I'll stand away from the microphone so as to not deafen everybody, but it is a distinct pleasure this afternoon to introduce the second speaker in this year's President's Lecture Series, Professor Lynn Loo, who's currently, as Shirley mentioned, Professor of Chemical and Biological Engineering. She's also the Deputy Director of the Andlinger Center for Energy and the Environment. A little bit of background on Lynn. She is one of our own, having received her PhD from Princeton in 2001. Did a postdoc at Bell Labs after that, and then joined the faculty at the University of Texas at Austin. But we were very happy to be able to recruit her back to Princeton as a faculty member in 2007. Lynn has launched and continued a program of research in electrically active polymeric and molecular materials, and in the development of innovative processing technologies for the realization of low-cost, lightweight, mechanically flexible devices, such as organic transistors and solar cells, many of which you'll hear about today. She's been recognized for her pioneering innovations with a number of awards. These include, for example, just some recent ones here, the Colburn and Owens Corning Awards from the American Institute of Chemical Engineers, the Dillon Medal, and also being elected a Fellow of the American Physical Society, a Sloan Fellowship in Chemistry, and has also been named a Young Global Leader by the World Economic Forum. And so I'm very fortunate to have Lynn here today to tell us about ubiquitous electronics through conducting plastics. So, Lynn?
Thank you, Rick, for that very generous introduction. This President's Lecture, as if it could, right, has just gotten better because I was just introduced by my very own thesis advisor. He didn't tell you that. Before I begin, I'd like to thank a couple of people. Shirley Tillman, thank you for your leadership. In the 11 years you've been on campus, you've just done so much, especially for science and engineering. You've injected new energy and new resources for which we're all very appreciative. And you've been an excellent mentor to young women in science and engineering. So thank you for that. I'd like to thank Carter Bales and Silda Walt-Spitzer, who are here from New World Capital Group. This is where I'm spending my sabbatical this semester. And thank you for taking the time to come and spend the afternoon with me. And of course, Philip Chu, my husband, ironically, he's only seen me speak one other time. And as luck would have it, that one other time, I had to speak in Mandarin. And so I really fumbled horribly. So this, I see it as my opportunity to redeem myself. All right. So when we talk about plastics, these are the images that we conjure up, right? These are the ubiquitous, common commodity plastics that we think of. They're electrically insulating. They're used for food packaging. They're used for containers, for soda, for water, for chemical products, for cleaning agents. And they're also used as styrofoam for food packaging, which Mayor Michael Bloomberg wants to ban from New York City. Very rarely do we think of plastics that are electrically active. When you think of electrically active plastics, it really opens up a new paradigm of applications. So applications where you can make electronic skin. So this is a project at University of Tokyo by one of our global researchers, Takao Someya. He had used plastic circuits to make pressure sensors and network these pressure sensors together to make an electronic skin. Here, researchers at General Electric have used plastics to emit light, so you can use these as organic light-emitting diodes. Here, plastics that can absorb sunlight and generate electricity are used, so you can make solar panels. And in this case, on this flexible display, if you look at what drives this flexible display, the circuits are made of semiconductors that are plastics. In all these applications, what's unique is that they really call and use the attributes of organic semiconductors and plastics. They're all mechanically flexible, they're lightweight, and here, for example, you can shape the plastic arbitrarily to conform to different kinds of shapes and form factors. And so this is something that's very unique to the world of organic semiconductors and plastics. This is not something you can easily do with inorganic semiconductors like silicon and gallium arsenide. So this field was really credited to these three gentlemen here. Alan McDermott, Hideki Shirakawa, and Alan Heeger shared the Nobel Prize in Chemistry in 2000 for discovering that under certain special circumstances, you can make plastics conduct electricity. So during this time, I was just about to finish my graduate thesis here, and I was really inspired by the Nobel lectures that these three gentlemen gave. And so I decided that for my research program, what I would like to do is to apply the polymer chemistry and the polymer physics that I've learned from Rick Register to this new world of materials. So our group, we're interested in using carbon-based molecular materials and polymers to make electronic and optical devices. And of course, this leverages the unique attributes of this class of materials. Compared to inorganic materials like silicon and gallium arsenide, organics are chemically versatile. With relatively straightforward chemistries, you can, for example, tune the backbone of this compound, and by doing so, you can change the properties. In this example here, what we've done is add subsequent benzene rings, and this is the conjugated core. This is the electrically active component of the material. And by doing so, we're changing the band gap. And by changing the band gap, we can change the color at which these molecules absorb. And this may be useful if you think of organic light-emitting diodes, where you want to tune the light emission of your organic light-emitting diodes, or in photovoltaic or solar cells, where you want to tune the wavelength at which your devices absorb light. You can also use rather straightforward chemistry to add side groups to the molecule. And when you do that, you can now promote solution processability. The compounds are now soluble in organic solvents or even water. We routinely make conducting polymers in water. And so what you end up with are inks or formulations or paints that you can easily coat over large areas. So this dramatically makes the processing much more straightforward. These are organics after all, so they're mechanically flexible and they're lightweight. So you can envision applications like I've shown you here and the applications that we talked about earlier on. So collectively, with all these attributes, you can, for example, make polymer photovoltaic membrane that can sit conformably on this undulated roof. It can then collect sunlight and generate electricity to power a local display, for example. So the kinds of chemical compounds that we work with, some of the representatives are shown here. And what's common amongst all these chemical structures is that they have a lot of carbon-carbon double bonds. These are the double bonds. And these carbon double bonds have pi orbitals. And it's really when these pi orbitals overlap between neighboring molecules that you can get charge to transport. And so if you make a macroscopic device, you want the molecules to organize on a large scale so you can get charges to hop from one molecule to another through these pi orbital overlap. Now, as exotic as these molecules may look, some of these are actually pretty common. So this copper phthalocyanine, for example, is a common dye or a pigment that can be found in house paints or automobile paints. If you take this copper phthalocyanine and we decorate the copper phthalocyanine with fluorines, fluorine is electron withdrawing. So what we've effectively done is to lower the energy levels. So now this compound, it's more easy for us to inject electrons in this compound compared to this one. So this has a higher tendency to transport electrons. Other organic semiconductors include this buckyball, or this 5-fused benzene rings. It's called pentacene. We've also looked at naphthalene diimide, pyrrolene diimide. And now this compound looks very similar to this guy. It's also a pentacene, so it's a pentacene derivative. we've added bulky side groups. And if you recall the slide earlier, the purpose of adding these bulky side groups that are electrically insulating is to now promote solubility. These side groups are so bulky that it disrupts the van der Waals interactions. Now this goes into solvent, whereas this one doesn't. And then finally, we've got polymers that we work with. N here's the number of repeating units. And it's not uncommon that N can be 30, 40, 50, which means that the conjugation, the electrically active core, is pretty long. And if you recall in the previous slide, when the electrically active core is long, we narrow the band gap. And so we can tune the optical and electronic properties by changing the molecular weight of these polymers. This was one of the first projects that I got involved with in this area when I was a postdoc at Bell Labs. So here, shown below, is an electronic paper display. This was built on a plastic substrate, so it's a display that's bendable and flexible. So mind you, this was in 2001, so way before the Kindles and the iPads, right? So the electrically active component is really in the circuit of this display. So if you peel off the protective layer, you peel off the emission component, you'll find the circuits, and that's where the organic semiconductor is. So in the circuit level, you've got transistors. Transistors basically act like switches. They turn on and off. And when your transistor turns on, it charges up this pad. So you induce an electric field. This electric field then forces the electrophoretic ink, the microcapsules in this ink, to float to the top. You get a white pixel. When you turn off the transistor, this field dissipates, and these tiny little white capsules then sink to the bottom, and you get a black pixel. So by turning on and off your transistor, you're basically turning on and off your pixel. So on, white, off, black. Okay? And so in this display, there are 256 pixels, controlled by 256 of these transistors. Each transistor can independently turn on and off, so your pixels can be independently white or black. And so this is called an active matrix type of a display because you can individually control these transistors. So a little more about transistors. So this is a side view cartoon of what a transistor looks like. It's got 3 electrodes. It's got the gate electrode, the source electrode, and the drain electrode. This is the organic semiconductor. So this is the organic plastic that we're interested in. Okay? And it's separated from the gate by this gate dielectric. This semiconductor is an insulator when we don't apply any gate bias. But when we apply a gate bias, we get charges to accumulate at these interfaces. And this opens up a channel for now charge to flow from the source to the drain electrode. I'm a chemical engineer, so I like to think of this device like as though it was a valve. And the analogy between a transistor and a valve is in how you turn the valve on, right? When you open the valve, this is like applying a gate voltage. You allow water to flow through the valve or current to flow from the source to the drain electrode. To characterize these transistors, one looks at the source-drain current as a function of source-drain voltage. And this series of curves basically is with increasing gate voltage. So as you increase gate voltage or as you open your valve, you get more and more current through. The switching characteristics of the transistor is more obvious if you look at the source-drain current as a function of the gate voltage. So this is where the valve is closed, right? No current. And when you open the valve, water starts flowing or current starts flowing, so this goes up. And then eventually, when the valve is completely open, it saturates. So this is the on state, and this is the off state of the transistor. So for the backplane applications that I was telling you about in electronic papers, there's a figure of merit that one looks at. One looks at the mobility. And the mobility basically measures how effectively charges are transported across this channel. And so a mobility of 0.1 to 1 centimeter squared per volt second is what one looks for these types of application. So now so that's a macroscopic view of transistors. Now I'd like to zoom in and look at the organic semiconductor itself. We talked about this pi orbital overlap, and we said that you need extensive pi orbital overlap in order to facilitate charges to transport from one molecule to the next and next, right? So one can envision that how the molecules are organized in this organic semiconductor layer critically affects device characteristics. So let's say if we had pentacene, right? This is the molecule that we're looking at. Its pi orbital overlap is now in this direction. And so this, presumably, is good for charge transport because the pi orbital overlap direction is commensurate with the charge transport direction. And so I'll come back and talk about structuring of these molecules. Right, so our group is interested in processing, structure, function relationships, okay, of these materials. So these are van der Waals solids, meaning that they're actually very heterogeneous across many different length scales. And so it's critical to control the structure on all these different length scales in order to optimize device characteristics. On the molecular length scale, down at the molecule level, one worries about how these molecules are packed relative to each other because there's this pi orbital overlap. But let's not forget, we're making devices, right? So we need to think about relevant length scales associated with these devices. If we look at thin film transistors, for example, there are two relevant length scales. One is the thickness of the film. That's about 100 nanometers thick. Okay, that's here. And then, of course, there's the width of the film, right? The length at which charges have to transport from one electrode to another electrode. So along the depth of the film, one worries about whether the molecule is lying flat or whether it's edge-on. When it's edge-on, the pi orbital overlap is in the lateral direction. That promotes charge transport. When the molecule's edge-on, the pi orbital overlap direction is in the vertical direction. That promotes charge transport in the vertical direction. Okay? So being able to control this is important. Along the length of the film, one then worries because when you have this, or when you can get the molecules to organize, or what we call crystallize, they form these crystals, but this length scale is very large. So often, this macroscopic film has multiple crystals that then meet each other and form a boundary. So then the question becomes, what happens at that boundary? Do charges get trapped at that boundary? What happens? Okay, so structurally, it's very, very heterogeneous. And what I'd like to do is to show you two examples of how we can control the outer plane molecular orientation and the in-plane molecular orientation. So we'll talk about this one first. So to look at the outer plane molecular orientation, we've chosen to look at this compound. This is hexabenzochoronine. It's a contorted species. I should mention that this is a work of Anna Hispansky, who's sitting right there. Leo Shaw was a senior who graduated last year and is currently in the graduate program at Stanford. He won the McCracken Prize for his thesis with us. Jessica Sailors is currently a senior who's doing senior thesis here. And this work is being continued by Nicholas Davey. OK, so this is hexabenzochoronine. If you look at the chemical structure, there are lots of double bonds. Again, so there are lots of pi overlap, or there can potentially be lots of pi orbital overlap. If you look at the side view of this molecule, you'll see that the external benzene rings are all puckered out of plane. That's why it's called contorted. Okay? And because it's contorted like this, when you deposit it as a film, they have a hard time organizing themselves because it's contorted like this. And so they actually don't exhibit very much long-range order. And so we call that amorphous, okay? No long-range order. And so as you would expect, because they're amorphous or they don't exhibit any long-range order, the devices that we make with this molecule is actually pretty bad, right? You would expect that because there's minimal pi orbital overlap. But what this film gives us is an opportunity for us to come in and think about how we can crystallize a film in a very controllable fashion so we can direct its growth. And that's exactly what Anna has done. She's come up with multiple ways to crystallize this film. So again, you deposit it. It exhibits no long-range order. But what you can do is you can contact it with a silicone rubber stamp. So this silicone is the same silicone that you buy from Lowe's or Home Depot and you caulk your bathtub with. We make a stamp out of that. We cure it. We make a stamp out of that. And we put that on top of this film surface. So it turns out that when you cure it, you don't ever fully cure the silicone. So you've got residual oligomers. Those leach out, and they can induce crystallization of your organic semiconductor thin film. So this is an optical micrograph under the regular optical microscope. And this is an atomic force micrograph that we can collect that's higher resolution than this, so you can zoom in and look at the features. It turns out we can take that same film, we can heat it up, and when you heat it up, you give it thermal energy, and so these molecules can reorganize, and they can crystallize too, okay? And the third method she's found that works is if you expose it to a solvent vapor. Again, the solvent vapor plasticizes the film, the molecules reorganize, and they crystallize. Now, what you'll notice is that the crystallization habit is actually quite different. The structures actually look quite different. But nonetheless, these films are all crystalline. So then Anna goes and makes transistors out of these films. And what she finds is as follows, right? Remember, mobility is how efficient charges are transported across that channel. If you have the as-deposited film, the mobility is low. Okay? But these three films are crystalline. Yet you'll see that their mobility is dramatically different. So this suggests that there's a difference in the structure due to the differences in processing. So to look at this further, we employ a lot of X-ray diffraction. So this is an X-ray diffraction pattern. We collect these at the synchrotron. So the students actually go to Cornell, where there is a synchrotron, and they run these experiments. These experiments basically give us quantitative information about the structure. Okay? So if we have HBC that's amorphous, and we expose it to this organic solvent vapor, we get an X-ray diffraction pattern that looks like so. You can see rings, and the fact that you can see rings indicate that this film is actually crystalline. There's now long-range order. Okay? What we can also do is we can take a single crystal of this material, and we can figure out the single crystal structure. We can then compare this X-ray diffraction pattern against that from single crystal, and we confirm that this HBC, when it's crystalline, adopts this P21C crystal structure. So what that basically tells us is how these molecules are organized relative to each other. Okay? From this X-ray diffraction pattern, you'll also notice that the intensity along these arcs are not uniform. You see, for example, in the 100 reflection, that it's slightly more intense in the equator, and in the 120 reflection, that it's more intense here. We can take this X-ray diffraction pattern, and we can run through our analysis, and we can plot the intensity as a function of azimuthal angle. Okay? And using that data, we can compare it against our single crystal data. And what we figured out is that what Anna figured out, is that these molecules are actually oriented flat on, so like I've cartooned here. Okay? And so when the molecules are oriented flat on like this, the pi stacking direction is generally in the vertical direction. So it's no wonder that this film, although it's crystalline, the mobility is not that much higher than the mobility of a device that has these amorphous film. Okay? So what happens when you look at the film that's been crystallized against a silicone rubber stamp? Well, the X-ray pattern looks very, very different. Instead of rings, what you see are spots. The spots indicate that the film is highly oriented. So the molecules are very, very oriented. And again, by doing that same analysis, what Anna figured out is these molecules are actually oriented edge-on. Okay? So when they're oriented edge-on like so, their pi orbital overlap direction is in the lateral direction, and that's in the same direction as you would like to transport charge for thin film transistors. So it's no wonder that these films exhibit high mobility. So we can sum up what we found by plotting mobility as a function of this F100. This is Hermann's orientation function. It's basically a parameter that can quantify the extent of orientation in our film. So 0 means there's no preference, or it's disordered, or there's no long-range order. Negative means there's a preference for molecules lying down. Positive means there's a preference for molecules standing up. And you can see a direct correlation between the mobility and the orientation of the molecule. And I think what's nice about this, this work is that Anna can now dial in preferential orientation. If you want to make transistors, you should make them this way because they have high mobility. But on the other hand, if you want to make organic light-emitting diodes or organic photovoltaic cells or solar cells where the electrodes are vertical, so you want charge transport to be in this direction, you probably want to make devices that look like so. And this is something that she can dial in now. Okay? So in the other example, I'd like to zoom out and talk about a larger length scale. So here we're looking at film between the electrodes. So in this example, I'd like to talk about acenes, and these are soluble acenes. So here again, this is the electrically conjugated core, okay? And these bulky side groups are added to promote solubility. What we've learned over the years is that it strongly depends on the size of the bulky side group relative to the conjugated core, and that determines how these molecules pack in the solid state. So over the years, what we found is that if the bulky side group is relatively small compared to the conjugated core, we get a 1D slip stack type of a packing. So this is basically top view of the molecule. So this is the top of this bulky side group, and this line here is this conjugated core. So because the conjugated core are aligned this way, charge transport and pi overlap is better this way. Okay? So it's a 1D slip stack type packing. Now if you make this bulky side group about half the size of the conjugated core, the packing reverts to this 2D brickwork type stacking. So you've got pi stacking in 2 dimensions. And then when you make the bulky side group huge compared to the acene core, you revert to this 1D slip stack type of a packing. Okay? And we've learned this over the years with John Anthony. We've been collaborating for about 10 years now. He's at University of Kentucky, and he's a wizard at making these things. It's like Legos. He just puts them together for us as we request. This is work of Kim Dickey, who graduated in 2007, who's now at a startup company called Nanoterra, and Stephanie Lee, who just graduated and is a postdoc at NYU. Okay, so unlike that hexabenzochroinine that I showed you earlier on, this compound actually is soluble. So we can put it in a common solvent, and then we can cast a film out of it. And that's what we do. So this is the solvent, and this is the molecule. Oh, sorry, I failed to mention. This is the molecule that we're going to talk about. This is triethylsilylalethenial anthradithiophenol. We're going to call it TESS-ADT for short. Okay? Try saying that 3 times fast. So we have this molecule. It's in solvent. We can cast a film out of it. And when you cast a film out of it, you can see that this film is featureless, okay? Just like before. There's no long-range order. But what Steph and Kim has done is they've exposed the film to a solvent vapor, this time 1,2-dichloroethane vapor. This vapor basically plasticizes the film, and now again induces large-scale crystallization and ordering within the film. So I don't know whether you can see it. The contrast is pretty bad. How this happens. So this is during the solvent vapor annealing process. So I'll run it again. So when we expose the solvent vapor to this film, it crystallizes. It starts out as a nucleation point, and then when crystallization happens, it basically radially spreads out. Okay? And so now this is all crystalline, and as it grows until this spherulite basically impinges on the neighboring spherulite, and so you form a boundary. Okay? These things are called spherulites because they start out round. Okay? We can track the radius as a function of time, and so we can extract a growth rate. Now, we can make transistors out of these materials. So we start out with this TESS-ADT that we spin coat or we cast as a thin film. The devices are pretty bad, again, because there's no long-range order and minimal pi stacking. But if we crystallize the film by exposing it to solvent vapor, you can see that the mobility increases by 100 times. Okay? And now this mobility is relevant for the kinds of applications I was telling you about. So the story remains that you've got a film, right? So this is a top view of a transistor. You've got electrodes, and then you've got TESS-ADT that we've coated everywhere. And now you expose it to solvent, and it crystallizes. And you can see the structural heterogeneity here. There are lots of boundaries, right? Because these spherulites meet. So the question becomes, well, what is the role of these boundaries? Do they adversely affect charge transport? So to study that, we need to first figure out what the role of the grain boundary is. So what we did was we basically seeded the crystallization process so we can control the size of these crystals. It starts out at about 3 millimeters, but as we seed the crystallization, we can get sizes down to about 30 microns, which is half the width of your hair, right? So we can span the length scale here. And then we can make transistors and test their mobility and plot it against the size of these crystals. So the distance between the electrodes stays constant. If we change the size of the crystal between the electrodes, what it means is we're also inversely changing the number of boundaries within these two electrodes. So here we have lots of boundaries. Here we have minimal boundaries within the transistor channel. And you can see that mobility actually increases as you decrease the number of boundaries or as you increase the crystal size. So clearly, the boundaries have an adverse effect on the device characteristics. So I'm showing you a cartoon, but there was a lot of X-ray work that's gone on for us to figure out what this cartoon looks like. So this cartoon shows a spherulite, or 3 spherulites. These are the nucleating point of the spherulites. And when you expose them to solvent vapor, they grow. And they grow in such a way that the molecules are always edge-on, okay? And the molecules basically steadily march along basically in the radial direction, okay? So that's what the molecules look like. So this is the pi stacking direction, okay? It goes radially outwards. So the molecules grow until they meet at a boundary. Now there are 2 different kinds of boundaries. There's what we call a low angle boundary, where the orientation across that boundary, the mismatch in orientation is small. There's also a high angle boundary, where the orientation mismatch across that boundary is large. So how do we decouple the contributions from high angle boundary and low angle boundary? Well, it turns out that we can control the growth rate. And so I'm going to show you a pretty clever patterning process that Steph came up with. So like I showed you before, we can measure the growth rate of test ADT on these different substrates. And so on silicon wafer, the growth rate of test ADT is about 25 to 27 microns per second. It turns out that we can decorate this substrate with different kinds of chemicals before we deposit test ADT, and then we solvent vapor expose it to get it to crystallize. And if we do that, we can reduce the growth rate. So these spherulites, the video that you show, the growth rate is much slower if we decorate the surface. Okay, so this is a hydrophobic surface, and now the growth rate is 10 microns a second. If we make the surface very, very hydrophilic by decorating it with something else, we can also reduce the growth rate. Okay? So because we have this difference in growth rate, we can now exploit this difference to pattern our film. So we start out with a channel now. Okay? This is silicon, so in here, the growth rate is fast. And then we've basically patterned it such that out here on the boundaries, the growth rate is slow. So now I'm going to show you a video of what happens when we expose it to solvent vapor. Instead of forming these round spherulites, we're now guiding crystallization along a channel. Okay? We've broken that radial symmetry. So what we can do is design patterns, okay, to guide the way these crystals are going to meet. So again, growth is fast here. Growth is slow on the orange regions. Okay? Growth is fast in the yellow regions and slow in the orange region. And so now we've coated the entire substrate with this test ADT. We're going to expose it to solvent vapor, and you're going to see the growth process. So here, the growth occurs like this. And here, the growth occurs like this. And so we've been able to engineer in a low angle boundary. And here we've been able to engineer in a high angle boundary. Now that we've been able to isolate these 2 kinds of boundaries, we can come back and study their contributions to charge transport. So what Steph did was she evaporated a gold pad. This is 1 electrode. And then she uses conductive AFM as the 2nd electrode. And she basically probes across this boundary. And each time she makes contact, she collects the current. And so you can make a current map. And so this is the current map across a low angle boundary. And you can see that the current differences are small. But when you probe the current map across a high angle boundary, you can see that the current drop is actually pretty large. You can assume a model of resistors in series and back out the resistances. And it turns out that these kinds of boundaries are twice or more than twice as resistive as these kinds of boundaries. So that's telling us that if we want device uniformity, you don't ever just make 1 device. You make many, many devices over a large area. You want to try and avoid these kind of boundaries But these kind of boundaries are OK, right? And so here I thought I would show you a cute study of what we've done. So again, growth is fast in the yellow region and slow in the orange region. And instead of, again, growing these round spherulites, we can now guide the crystallization process around corners and bends. And you can see it grow. And it's going around corners. And that's purely from imposing a different surface chemistry on the substrate. So again, this is something that the experimenter can completely control. Okay? So before I end, I thought I would show one last example. And since the group, actually half of the group works on solar cells, I thought I would show you an example of structure engineering in solar cells. So this is work of Jung-Bok Kim, who was a postdoc in the group, and he's now a senior researcher at Korean Institute of Science and Technology. So here I'm showing you a picture of a leaf. Okay? We know that leaves take sunlight and convert sunlight into chemical energy. Well, the analogy is solar cells. It takes sunlight and converts sunlight into electrical energy. Now, the leaves have plenty of structure on the surface. And that structure helps internal scattering of the light. And it basically helps and confine the light where the photosynthesis centers are so you can be more efficient. So we thought, well, can we mimic that structure to make our solar cells more efficient? Before I show you our data, let me tell you a little bit about solar cells. So like I said, a solar cell, right, your electrodes are in the vertical direction. So this is your substrate. You've got one electrode here that's transparent, so sun can actually penetrate. And then you've got your second electrode, which we call the cathode. And the active plastics is really this pink and blue layer. One's a donor, the other one's an acceptor. And so light basically comes through and gets absorbed in the donor. These are the energy levels of the donor, so the lowest unoccupied molecular orbital and the highest occupied molecular orbital of the donor and the acceptor. So when you shine light and light gets absorbed by the donor, you generate what's called an exciton. An exciton is a tightly bound electron-hole pair. And that's very unique to organic materials because the dielectric constant in these materials is small. So this exciton migrates around until it finds an interface. When it finds an interface, then it splits into free carriers. And now these free carriers can then migrate to the external electrodes. So now you begin to appreciate why photovoltaic cells are inherently not very efficient devices. The overall efficiency of one of these cells depends on the efficiency with which light is absorbed. It depends on the efficiency with which excitons diffuse. It depends on the efficiency of charge transfer, and then finally charge collection at the external electrode. When all said and done, the record polymer solar cell has an efficiency of 10%, okay? Compared to silicon, which is now at high 20s, low 30s, all right? One can quantify solar cells by looking at the current density as a function of voltage. And basically, you want to look at this power generation quadrant, okay? So the bigger this area is, the more power you're generating, the higher the efficiency. Okay? So coming back to leaves and solar cells. So this is a magnified view of leaves, right? And it's got these surface structures. And so we worked pretty hard with Howard Stone in the mechanical and aerospace engineering to try and recreate these structures. And so these are our wrinkles. These are the natural wrinkles. And so we can try, and under different conditions, we can get different densities of these wrinkles on the surface. And so the idea is, again, to introduce these wrinkles to our solar cells to see whether we can boost the efficiency. So we've got our wrinkles, okay, and then we build our solar cells on top of that. So our active polymer is P3HT and PCBM, and the chemical structures are shown here. So you've seen P3HT earlier on. This is the polymer I was telling you about. Because of the relative energy levels, this guy transports holes. This guy is the buckyball that you saw earlier on, except it's got these things dangling off of it. And we put these dangling things because now, again, it's solution processable. So we can throw these two components in a solvent and make an ink out of it and cast a film. All right? And so this guy transports electrons. This guy transports holes. So we make our devices, and we measure the JV characteristics. If we were to make our device on a flat surface, we get this black curve. And so this is the power generation quadrant. It has a photocurrent of about 5 milliamps per centimeter squared. But if we make that same device on a wrinkled surface, you get this curve, so it's a bigger area now, and the current is now 7 milliamps per centimeter squared. So by just introducing the surface structure on the substrate, we've been able to boost the current generation. To confirm how this current generation is boosted, we went to Nicholas Pegard, who's in Jason Fleischer's group in electrical engineering here, and he did some photon flux simulation of what's going on. So basically, we've defined our polymer layer, our absorptive layer. We've got a reflective aluminum electrode, and we shine light. So these red arrows indicate the light that we're shining, the flux of the light that we're shining. So on a flat surface, light comes in. It either is absorbed by the photoactive layer, or it gets reflected by this aluminum electrode, and it comes back. So the light path is once in, once out. Okay? With wrinkles, because the angle of incidence is now different, when light goes in, you can direct light within that absorbing layer. So light effectively spends more time in the absorbing layer, and so you have more opportunity for light absorption and photocurrent generation. So that's very, very similar to what happens in a leaf, where you have these structures, and these structures basically induce multiple internal scattering, and so the light spends a lot of time where the photosynthesis centers are, and it gets absorbed and generates chemical energy. One surprising, or one unexpected surprise was as follows. So here, I'm plotting the solar spectral irradiance, so the sunlight. This is what sunlight looks like as a function of wavelength. Okay? And so typically, when we use these polymers, we only absorb a portion of the sunlight. So we waste all the sunlight. So wouldn't it be nice if we can absorb all the sunlight too? So a lot of chemists have been designing low band gap polymers to see whether we can absorb this portion of the solar spectrum as well. So if we look at the external quantum efficiency, this is the efficiency at individual wavelengths, okay, of the device on the flat surface, you see that there's a sharp drop. This sharp drop is due to the band gap of the P3HT polymer. So it's an inherent materials property. You can't run away from that. That's inherent in the material we use. But now if you look at the device that we built on the wrinkled surface, that now looks very different, right? You can see non-negligible, actually substantial photocurrent generation beyond that edge that we were seeing. And that's because for those of you who make solar cells, that's because we believe what we're doing is we're directly exciting the charge transfer complex. And so we're getting light absorption and photocurrent generation beyond what's traditionally been limiting us in terms of materials properties. Okay? So I hope I've shown you that structural engineering is actually quite a nice thing. On multiple length scales, on the molecular length scales, we can control whether the molecules are oriented upright or lying down. And of course, we need to think about at the device length scales what happens. And then of course, you can do structural engineering on the substrate itself to really overcome the inherent limitations of materials properties. And going forward, I think this would be very useful in trying to overcome the limitations in organic light-emitting diodes, which we didn't talk about today in terms of lifetimes. When we look at transistors, uniformity across a large area is very important because you don't just make one transistor, you make an array of transistors. So all of them need to be performing at the same mobility. And of course, stabilization of the active layers in photovoltaics as well. Akin to Robert Redford in The Horse Whisperer, we like to think of ourselves as the molecule whisperer. We think we can control structure, we can understand structure, and by coming up with the right processing conditions, we can really coax the desired properties out of these materials. So in many ways, we see ourselves as the connector between the organic chemistry community, who are so good at designing and making these materials, and the electrical engineering community, who use these materials to make devices, because we can come up with design rules and guidelines where we can help together collectively make some advance in this field. So with that, I'd like to thank our funding sources that have allowed us to do the fun things that we do, and of course the personnel, past and present group members, collaborators on and off campus, at the synchrotrons, and industry, I have the privilege of working with a group of very driven, intellectually curious, and creative individuals. And it's really because of you guys that I'm standing here today. So thank you very much.
Thanks, Lynn, for a very stimulating and accessible talk. I'm sure there are some questions, so and we have time to take a few questions from the audience.
So maybe I'll start with the question as an ex-organic chemist. Thank you for the shout out to organic chemists. You know, one of the things organic chemists love to do is in crystallization, to be able to actually seed the crystallization, to seed it in a very specific place. And how easy is it to do when you're trying to take these amorphous films and essentially have the crystallization all moving in one direction as opposed to in multiple directions or being seeded from multiple sites?
So in crystallization, there's nucleation, and then there's growth. Growth, as I've demonstrated, is something we have very, very good control over. Nucleation is completely stochastic right now, and so we don't have good control over it. We're thinking about ways to control it by nucleating it with different kinds of surface chemistry, for example. But right now, nucleation is completely stochastic. So in the beautiful images that I showed you, where you have two crystals growing into each other or this way, well, Steph had to try multiple times before she got two crystals to grow. You need to basically seed two crystals at the same time. Yeah. So that's not straightforward right now. Yeah, that's a good question, though.
Saw another hand up. Yeah.
That was my question.
Oh.
There's another hand up behind you, Bruce.
You mentioned the Nobel Prize work on conducting polymers.
Yes?
Could you briefly discuss what was it that you found? How did they come up?
Oh, sure. So, so Alan Heger and Alan McDermott and Hideki Shirakawa basically worked with polyacetylene. Okay, so it's double bond, double bond, double bond, and it keeps repeating itself. And so what they found is if they doped it, they exposed it to iodine, they can get an electrically conductive polymer. And so this polymer no longer just looks like polymer. It's actually shiny. It's got a sheen. It actually looks like metal. So it's this doping process that they discovered. So it's normally an insulator. If you expose it to iodine, you can get a conductive polymer.
As I understand, you're trying to orient the microgroups so you get high conductivity. And what you're trying to do is minimize grain boundaries and
Yeah.
crystallinity.
Well, minimize high angle boundaries.
Yeah.
Low angles, we don't care.
So how does that affect the ductility or flexibility of the films?
That's a good question. These films are only about 100 nanometers thick. So really, the ductility or the mechanical properties of your device, that's not the limiting factor. So frequently when we make solar cells, for example, the limiting factor is the indium tin oxide that we use as an electrode. And so we have a small effort in the group that's trying to replace indium tin oxide with a conducting polymer. So now you have all polymers. So that's often what's limiting. It's something else. It's not the active material itself because it's so thin. Yeah.
Questions?
Brian.
Brian.
In order to induce the surface orientation, is there any scope of use of Langmuir logic on that?
Yes, we thought about that. Then the difficulty becomes trying to scoop it out from the Langmuir-Blodgett trough. That's one issue. And I'm sure that we can overcome, right? That's just learning how to do it. The other issue is water. And so water is frequently something that we would like to avoid when you have hydroxyl groups at the interface where charges transfer. It acts as electron traps, and so it can trap electrons. Oh, I said that twice, but yeah. Oh.
I was trying to understand one graph you had where you showed the change in mobility as a function of basically the size of the crystallites, right?
Correct.
And so that was changing the number of grain boundaries you have. And it was strange because it seemed like the size varied by 2 orders of magnitude and the mobility only that
Yeah.
by a factor of 4.
Right.
Do you understand?
So it's because it's I might have taken out the line, but we can model that, and it's basically a weighted function. The mobility is a weighted mobility of the inherent mobility of the grain, and then the mobility of the boundary, scaled by their respective lengths. And here, the mobility of the grain itself is not very high to begin with. So you're limited at about 0.4. So we've made, for example, because these spherulites we can grow pretty large. We can grow up to about 3 millimeters. And so we would grow a spherulite to about 3 millimeters, put lots of electrodes on a single spherulite. And so we can measure the mobility as a function of even orientation, right? Because these grow radially outwards. And we've done those measurements. And as a function of angle, the mobility is all about the same, and it's about 0.4. And we think, talking to John Anthony, we think the inherent low mobility of this material is because if you look at the chemical structure, maybe I can go back real quick. Oh, sorry. So if you look at the chemical structure of this guy, right? There's one sulfur on this side and one sulfur on the other side. That, and when the sulfur is on the same side, that's scrambled. And so when we get a macroscopic sample from them, we've got two, is it isomers? And then isomers? Isomers. So we get those two isomers. I'm testing, Shirley. So we get two isomers, and you can't easily isolate them. And so that creates inherent disorder within even a single spherulite.
So the low mobility is basically grain boundary dominated.
The low mobility is grain boundary dominated, and the high mobility is dominated by these kinds of local disorder that we can't get rid of. Plus, a spherulite is not, if you think about a single crystal, you know how the molecules are exactly oriented within a single crystal. A spherulite is not a single crystal per se. There are lots of low-angle grain boundaries in it, right? So if I go back to this cartoon, right? So if you look at how the molecules are oriented, there are slight variations in the angle the molecules are oriented. So this is actually a low-angle boundary. So there are lots of low-angle boundaries within a spherulite. So that limits the mobility too.
I'll take the moderator's prerogative. So in the wrinkling for the solar cells, is there some optimal wavelength for the wrinkles?
Absolutely.
And what is that, and how does that compare to a real leaf?
Oh, that's a good question. We never compared it to a real leaf, but there is an optimal wrinkle density, if you will. And the reason for that is because when you have these wrinkles and folds, you can guide light in, but they're symmetric. So if you can guide light in, you can guide light out. Mm-hmm. And so you want to space them far enough apart that you can guide light in, and it has an opportunity to be absorbed before you guide light out. And so if you have too many of these wrinkles all very close together, light goes in, light comes out. And so then you see if you plot current as a function of wrinkle density, it goes up and it comes back down. So there's a sweet spot.
And it's basically the absorption length of the...
Yeah. It's 1.8 microns, I think. I forget the details. And then maybe 10% folds or something like that. Yeah.
Yes.
Hi, my name is Christopher Gordon. I'm a sophomore in the CB department.
Hi.
Yeah, it's really amazing.
Thank you for coming.
Thank you. It's really amazing how by altering the structure of these materials, they can change their properties.
We think so. We think so.
So I was wondering, what's the group's next main thrust?
They're all sitting right there. You can ask them. Anna has some pretty amazing. So I've only shown you a snippet of what's going on. So with this hexabenzochroranine derivative, the synthesis is actually very modular. So we can add all sorts of different functionalities to the external periphery. So one project that we're looking at, for example, is if you look at this HBC. Sorry, I keep coming back here. So we can decorate the we can decorate these peripheral aromatic rings with different substituents. And by doing that, we can lock in these contortedness. And so we're trying to see how this conformation then affects how it packs and then about device performance. Okay? So, I mean, the synthesis is very modular. So we can buy different reagents and we can decorate the external with different kinds of chemical species. So we're systematically going through those to see what happens. And then Nicholas Davey is trying to look at, instead of 5 rings across here, we've now got 7 rings across here. So what happens when you have 7 rings across here? Because now that, again, changes the conformation. Okay? Yeah.
Any questions?
Can I ask the last?
Oh,
You see the plastics coming in the VLSI world?
sorry, I can't hear you.
You see the plastic conductors coming in the VLSI, that landscape introduced circuits.
That's a trick question. I think it has a place, not in VLSI probably, because these plastics, at least the conducting polymers that we work with, that I didn't show any results from, the ones that show metallic type behavior, ohmic behavior, okay? So they're conducting polymers. They're acidic, and so that acidity is a big issue when it comes to CMOS integration in VLSI. So I think you need slightly different chemistry probably.
I think we will let the president have the last question here.
So you've been spending your sabbatical thinking about the world of finance, and so the question is, would you advise someone to invest in a solar cell company at this point?
The answer, Carter, you can tell me whether I'm right. The answer is probably no. Oh, he nodded his head. So the issue is silicon solar modules have gotten so cheap these days. If you look at the learning curve, which I actually showed the graduate students at the high table dinner discussion yesterday, if you look at the learning curve of solar module prices for silicon, it's dropped so fast that, I mean, it's steeper than anyone would have predicted because the Chinese have learned how to make these modules so well that they flooded the market with so many solar panels. So right now, the issue is the modules are already at very, very cheap cost. And so here, for example, we shouldn't argue that we're making low-cost solar panels, because that's not going to go anywhere. I think what we should argue here is that we can make solar cells that have very different attributes. So we can cover curved surfaces when silicon can't. These guys are semi-transparent, so you can think about window-integrated photovoltaics, whereas you can't do with silicon. These guys, they actually absorb diffuse light. They don't need intense sunlight. And so you can think about indoor uses of solar panels. Well, I guess they would be light panels as opposed to solar panels. So you should focus on the unique attributes of these technologies as opposed to competing head-on with silicon, because silicon's just so cheap now. Yeah. Was that good? All right.